Welcome to our Chapter 15 lecture video. Today we're going to talk about chemical equilibrium. We'll talk about a few other things in additional to equilibrium, like kinetics. Kinetics is how things happen. Equilibrium is what happens at the end of the day. So reaction rates is a part of kinetics, or how things happen. Equilibrium in those calculations are about what happens at the end of the day when everything is said and done. We have a formal definition for equilibrium where the forward reaction equals the reverse reaction. The forward reaction would be the products react to make, or sorry, let me say that again. The starting materials react to make the products. The reverse reaction would be the products react to make the starting material. Le Chatelier's principle is just a theoretical idea of how we can disrupt equilibrium or push it to the products or the starting materials, depending on what reaction we want to favor, the forward or the reverse. So dynamic equilibrium is this new concept. I apologize here. This should be a reaction arrow. Dinitrogen tetroxide turns into 2 molecules of nitrogen dioxide. This would be the forward reaction. Nitrogen dioxide turning into dinitrogen tetroxide would be the reverse reaction. The book uses a freeway to kind of show that if the flow of traffic goes in the same rate in one direction as it goes in the other direction, the amount of movement between the two areas is about the same, or it's in a dynamic equilibrium. So we often refer to equilibrium as the sense of sameness when everything is equal to each other, when you don't see any difference occurring or any change occurring. That's because the forward reaction equals the reverse reaction, and there's no apparent difference at the macro scale. Things are changing at the micro scale. If you could zoom in, you could see that things are constantly in flux. But on the macro scale, what we're able to interact with, it looks like everything is just at a standstill, or everything has this sameness or consistency. So we mentioned that we're going to talk about a little few things in addition to equilibrium, but the reaction rate is related to the kinetics, not necessarily the equilibrium. So reaction rate is how fast something happens. Equilibrium is how much of stuff do we have at the end of the day. So the reaction rate can be modified in a couple ways, but in general, faster reaction rates lead to faster reactions. Slower reaction rates lead to slower reactions. If something's slower, sometimes you can control it faster, but not always. Depending on what tools you have available, you may or may not be able to influence things. Collision theory is how we determine what kinetics actually does, because collision theory says that particles have to collide in order to interact. If they don't collide with enough energy or the correct orientation, nothing is going to happen. So if they collide with the correct orientation but insufficient energy, nothing happens. They just bounce off. If they collide with the correct energy but improper orientation, then at least not the reaction that you're concerned with is going to happen. Maybe something else happens if it has enough energy for something else to happen. But if it doesn't have the correct orientation and the correct energy, the reaction that you desire will not happen. This is a statistical process, and the amount of energy needed to cause a chemical reaction is called the activation energy. If you have more than the activation energy, or the exact amount of activation energy, you can pass from the starting materials to the products, depending if you're doing the forward reaction or the reverse reaction. And if you have less than the activation energy, you'll just never be able to get over that energetic barrier. So the most important way that we can modulate the reaction rate is pressure, temperature, and concentration. Concentration and pressure have the same effect as they cause particles to interact more. Pressure forces these particles together, whereas concentration just includes a whole bunch more particles in a smaller unit space. Temperature is related to the internal energy. There are other ways that we can add energy, like adding an electrical current or some other type of input, but typically temperature is the easiest way to raise the energy of a molecule. If you raise the energy of the molecule, you're more likely to be over the activation energy threshold. So we kind of already said all of this, but to spell it out in words, reaction rate is affected by concentration because it increases the amount of things there the statistical chance for more things to interact when there are more things is just higher. If you have two particles and there's a billion miles between them, it doesn't matter how reactive those particles are with respect to each other. They're probably just never going to interact. But if you have marginally reactive particles and they're just slammed into each other right next to each other, they can't get away from each other, then it's likely that you're going to have a faster reaction rate, even though it's a less energetic reaction. So as we increase the amount of particles, these amount of particles will interact more, and so more successful reactions will just occur statistically. Temperature just increases the energy, and so more of those collisions will be successful per collision. And so we can have the same amount of molecules, but if we slam them together harder, they're going to be in the correct orientation the same number of times, or percentage-wise. The particles will move faster because temperature increases, but there's just going to be more successful interactions. So pressure has the same effect that concentration does. Pressure is a little harder and much more dangerous to control than temperature or concentration. And so typically that's more done in an engineering setting, but it does happen in chemistry labs as well. So we have this idea of dynamic equilibrium that we introduced. We had the cars flowing in the one direction and then an equal rate in the back direction. This is, the book's representation of dynamic equilibrium. We're going to think of it as the forward reaction equals the reverse reaction. If I have some chemicals A plus B going to C plus D, that would be the forward reaction. The reverse reaction would be C plus D goes to A plus B, just the opposite. Sometimes this is called the microscopic reverse, but we more commonly refer to it as the forward reaction and the reverse reaction. It isn't that everything is in standstill. It's just that the amount of products turning into starting materials is equal in rate to the amount of starting materials turned into product. Just repeating what we've said. And so if you were able to track these molecules in solution, if you could put a 1 on this hydrogen and a 1 on that iodine and number every single atom, you would see that the atoms that are pairing together as time goes on, even though the concentrations have reached an equilibrium, they'll constantly be shifting partners. Now, this might be a very fast shifting, might be a very slow shifting. It just depends on the reaction. If you're doing an acid-base reaction, acid-base reactions or proton transfers are some of the fastest reactions that occur. Whereas, other reactions like the decomposition of a protein or something like that is very, very slow. So it all just depends on what type of reaction, what the energetics are. So the way that we define how much of a product or how much of a starting material we can expect to have at equilibrium is by this equilibrium constant. Now, the equilibrium constant is set for a given set of conditions at a given temperature, at a given pressure. And so the way that we formulate this KEQ is through a simple algebraic equation that is related to the chemical formula. So if we have some generic chemical formula like this, again, these are supposed to be reaction arrows. I must not have the correct drivers on my computer right now. I'll make sure to try to get those updated in the future. But we can generalize an equilibrium constant from this general reaction equation where we're going to take the products raised to their stoichiometric coefficients divided by the starting materials raised to their stoichiometric coefficients. So we would have something like this where we have D raised to its stoichiometric coefficient, C raised to its stoichiometric coefficient, and the same with A and B, the reactants. We want to make sure that we do this with the concentration, so this is always in molarity, moles per liter. And so that's why we've introduced this unit. It's why we want to get comfortable with some of the calculations. You're going to need it especially for this chapter. So if we had some decomposition reaction, nitrogen pentoxide turning into nitrogen dioxide and oxygen, we could set up the KEQ like this. Again, the products raised to their stoichiometric coefficients. If it's just a 1, just like every other case, you can leave it applied. We don't write, a 1 in front of oxygen or a 1 behind the nitrogen. It's just implied, just like always. And then the starting materials raised to their stoichiometric coefficients. And then we can plug into the calculator, assuming that we have these values. The challenge question for this chapter will be you will be given one of these values. You'll have to use that one value and the reaction to back out what the other concentrations are and then calculate for KEQ. It's a fairly long problem, but it's just an algebra problem essentially. And, knowing KEQ, which KEQ will be given to you in terms of the generalized formula that we had in this slide. This is the generalized formula that will be given to you on the exam. So going back. In general, we can use KEQ to estimate how much of the product or how much of the starting material there will be left over. And so KEQs that are large, remember we have the products on the top and the starting materials on the bottom. So if the numerator is larger, we'll get a larger number. If the denominator is larger, we'll get a smaller number. So when KEQ is large, we can expect a large amount of products. When KEQ is small, we can expect a very low amount of products or a very large amount of starting materials. So here would be the KEQ number for HBr. Depending on what this number is, we could figure out what the KEQ is. If you watch this reaction, you'll figure out that it's very, very large. And so we could predict that, a lot of molecules. If we saw the, formation of nitrogen oxide, you would have a very different KEQ because this doesn't spontaneously occur. It's not a very favorable reaction. And so there's only a very low amount of this at any given time in the presence of nitrogen and oxygen, which is what our atmosphere is mostly composed of. Nitrogen monoxide is a very toxic greenhouse gas that has a lot of adverse effects on our lives and nature. So in general, if we have greater than 1, the forward reaction is going to be favored. If it's less than 1, the reverse reaction is going to be favored. If it's equal to 1, the amount of products to the amount of starting materials will be in about equal molar ratios. Now, that doesn't mean that A and B are exactly equal to C and D in the amount of moles. It's just the amount of moles of everything. So maybe you have 1 mole of A and 5 moles of B. Well, that will give you, 2 moles of C and 3 moles of D. We just want to make sure that they're about the same as what happens when you have a KEQ of right around 1. If you have a KEQ of greater than 10 to the 3 or 1,000, you can expect it to favor the products by about 99%. If you have a KEQ less than or equal to 1 divided by 1,000 or 10 to the minus 3, you can expect the starting materials to be favored 99%. Now let's get into our first exception to the general case that we're given. Whenever we have a pure solid or a pure liquid in a mixture, since these are pure components, we can't really consider what the concentration of these species are. So we set the concentration directly equal to 1. Since calcium carbonate is a solid and calcium oxide are a solid, these are not dissolved. If these were aqueous solids that were dissolved, we could then do the equilibrium concentrations and calculations for them. However, since we have a pure solid as a product and a pure solid as a starting material, we will only consider the concentration of the remaining products in this case, which would just be carbon dioxide. The KEQ would be exactly equal to the concentration of carbon dioxide raised to its stoichiometric coefficient. This is true with pure solids and pure liquids. Gases can be hard to define because if you can't capture all the gas, then you don't know what the concentration of that gas is. But that's an experimental issue rather than a theoretical issue. Pure liquids and solids pose a theoretical issue rather than an experimental issue. So here would be a simple equilibrium calculation where we were given the values of the 3 reagents, the 2 starting materials and the product. The only one that's going to have a stoichiometric coefficient is the product. So the product will be raised to the square or to the second power, and then the starting materials will just be their given concentrations. We'll plug this in, and then we can solve for the KEQ. If you wanted to do this in non-scientific notation, that'd be fine. The reason we have scientific notation here is to maintain the confidence and the clarity of our significant figures in this problem. Again, not an issue until we get back to the final. So for this upcoming exam, don't have to worry about sig figs. For the final, there'll be a couple questions where you have to worry about sig figs. Here's the opposite type of problem where we have the equilibrium constant and we have some of the concentrations. We're going to have to figure out what the concentration of the missing reagent is. So in this case, it's just one of the products. And so we can calculate everything. Since everything is a gas, we don't have to set anything to 1. If we had pure liquids or pure solids, we might have to set one of the coefficients or one of the concentrations equal to 1. But we just have everything in the same phase, nice and simple, rearrange the equation, plug in the given information. We always have equilibrium at a given condition. So this is at 100 degrees Celsius, and it's assumed to be atmospheric pressure. If it's not stated, it's always going to be atmospheric pressure. It's hard to change pressure. It's very easy to change temperature. So Le Chatelier's principle is a kind of concept of how can we shift equilibrium. So most simply, if we apply some stimulus to a reaction, the reaction is going to move away from that stimulus. If that stimulus happens to be attributed to the product, we're going to shift the equilibrium to the starting material. If that stimulus is associated with the starting material, it's going to shift the equilibrium back to the product. Whatever stress you apply, the system will equilibrate away from that stress. So, in the case of this reaction, if we add product, we're going to push the reaction to the starting materials or shift it to the left, as we have here. So as we make more product, we'll push the product back to the starting materials. So as there's more product, more of those products can undergo the decomposition or the combination reaction. The decomposition would be the forward reaction, the combination would be the reverse reaction. But since there's more N2O around, these products can come together. So if we add a whole bunch of N2O4, we'll shift towards the products. More starting material will give us more products. More products will give us more starting material. So again, if I add something to, if the stimulus is applied to the starting material, it'll equilibrate towards the products. If the stimulus is applied to the products, it'll equilibrate towards the starting material. The real question is, what do we ascribe the change to? Is it impacting the starting materials more, or is it impacting the products more? Volume and pressure are going to really stress this because we have to think about how many moles we have. If we increase the volume, we decrease the pressure. If we increase the pressure, we decrease the volume because we're assuming that we're holding everything stable except for the one change. You can consider multiple changes, but then that becomes a much, much more complicated problem. And you have to decide which factor is more impactful. We're not going to do that in this class. Just not going to do it at all because it's too complicated. There's too many variables to consider. So we're only going to take one change at a time and hold everything else constant. When I do this, I'm going to affect which way the equilibrium is shifted. So if I have more moles of a gas, and pressure and volume is almost always going to have a bigger impact on gases and a negligible impact on solids and liquids. And that's because, gases are compressible. There's a large amount of space in between them. And so the volumes and pressures are very dependent on, what's actually going on molecularly. Whereas with liquids and solids, things are always touching each other. So if you increase the pressure or decrease the volume or any other combination of things, you're just changing things on the margins rather than drastically changing things like you would with the gas phase. So pressure and volume changes are going to have the biggest effects on gases. We think their effects are negligible or essentially uneventful, not something that we have to concern ourselves with for the liquids and solid solutions. But with a gas, if we have more molecules on one side, more moles, or just more atoms, however, more equivalents, whatever metric you want to use, if we have more gases on one side, that's going to be disfavored by increasing pressure. Increasing pressure is going to favor the least amount of things. Since gases take up about the same amount of space, no matter how large their molecular weight is, we're going to favor the least number of moles. The opposite will be true as we increase the volume or decrease the pressure. If there's less force forcing these things together, there's more, stability for having more things to occupy that space. And so if we have low pressure or increase the volume, we'll favor the side of the reaction that has more products or more moles of stuff. So in general, if we have, it's not as simple with pressure and volume as it is with, increasing the number of products or increasing the number of starting materials. You have to actually analyze the situation and say, okay, which side is more favorable to have a higher pressure? Which side is more favorable to have a lower pressure? Or you can think of it in terms of volume if that's more comfortable. Once you make that, decision or identify whether there's more moles on the reactant side or the product side, then we can say how the equilibrium is shifted. Sorry about that. And so exothermic reactions and endothermic reactions are reactions that take in or give off energy. The most common form of energy is just heat. It can be an electrical stimulus. It could be sound. It could be vibration. It could be any type of energy. But the easiest way to get an increase in kinetic energy is to increase the thermal energy. Exothermic reactions can be thought of as having heat as a product. They give off heat. Endothermic reactions can be thought of heat as a starting material. They take in heat to get the reaction going. So if I add heat to an endothermic reaction, I'm going to push it towards the products. If I add heat to an exothermic reaction, I'm going to push it towards the reactants. So the Haber-Bosch process is an example of an exothermic reaction. Unfortunately, this reaction is done at very high temperatures. Industrially, it's done between 600 and 800 degrees Celsius, depending on the reactor. And so the addition of this extra heat actually pushes the equilibrium towards the starting materials and is an inhibition on this reaction. And so if we could take away heat from this reaction, remove one of the products, we could drive the equilibrium to the products as such. So if the stimulus is on the products, removing heat is basically giving a larger proportion of starting material than we have products. And so it's going to drive things towards the products. You can remove things from the products to drive it towards the products, or you can add things to the starting materials to drive it towards the products. Both result in the same event, shifting the equilibrium to a specific direction. So here, nitrogen dinitrogen tetroxide is an endothermic reaction to convert into nitrogen dioxide. So a little bit of energy has to be absorbed by this molecule to break the nitrogen-nitrogen bond. Once that happens, it's happy being, this brown gas instead of colorless gas. And so if we remove heat, we do the opposite, that if we add heat, it's just identifying whether you have an endothermic or exothermic reaction. We're not at a point where you can predict endothermic or exothermic, so I will always tell you whether it's endothermic or exothermic. You don't have to know if these things are, taking in heat or giving off heat. It will be shown to you. You just have to realize that heat is also sometimes abbreviated as the delta sign or the triangle. So if you just have a triangle all by itself in a chemical reaction, that's usually there to indicate that heat is being referenced. So here's a visual example. If we cool dinitrogen tetroxide, you can just see the dry ice. That's what they're using to cool this, is dry ice and maybe water. But definitely some fluffy dry ice in here. It's clear and colorless. Then as everything melts or dissipates, it starts to heat up, and we see more of the brown solution. And so, depending on how we shift our temperature, we can make more or less of the starting material or product, depending on what our actual application is. So, in general, exothermic reactions have heat as a product. If we add heat, we shift towards the starting materials. Endothermic is just going to be the opposite. Heat is a starting material, so we need heat to cause the reaction to go. If you add heat, you'll push it towards the products. If you take away heat, you'll push it towards the reactants. We can also think of this as shifting to the right and shifting to the left, but it doesn't matter as long as it's, consistent and makes sense. We've talked about some specialized equilibrium constants. So in chapter 14, we talked about Kw. Ksp is just another specialized equilibrium constant. In this case, we're talking about the dissolution of a solid into a liquid. Since we have solid calcium fluoride that goes towards calcium ions and fluoride ions that are solvated, we can set the concentration of calcium fluoride equal to 1. It basically nullifies its position in the equation, and we just get the numerator. Since all solubility reactions or dissolution reactions are converting from a solid or pure liquid into some dissolved species, you will never have a denominator in a KSP. It's just the concentrations of the products raised to their stoichiometric coefficients, if there happen to be any. So here's a whole bunch of KSPs. We can look at these and determine which are going to be more or less soluble, because the KSP is just like the KEQ. The larger the KSP, the more soluble it's going to be. So out of all of these chemicals, calcium sulfate is the most soluble, and copper sulfide is the least soluble. We can do that by just looking at the exponents on these numbers. This is a really small number. This is still a pretty small number, but by comparison to all the other numbers we have, it's the largest. And so just another series. We can see that, lead salts are much more soluble than magnesium salts or, silver salts. Just comparisons. You don't have to memorize these. These are just things that you would use. Or I could give you the concentration of dissolved analytes, and then you could calculate the KSP. Just like plugging and chugging for KEQ, KSP is just the same. 3, 2, 1. Now let's look at how we actually do these type of calculations, because it's very trivial if we just have the concentration of barium and the concentration of sulfate, plug and chug. We've done that type of problem already. We've done it a number of times throughout the year, just with different setups. But if I give you KSP, how do you figure out what the concentration of these two are? Well, when we have just a 1-to-1 stoichiometric ratio, it's nice and simple. We can set them equal to the same thing, because they'll always be equal to the same thing. And then we can take the nth root of the KSP, depending on how many things there are. Since we have 2 things, we'll take the square root. If we had 3 things, we'd take the cube root, 4 things, the 4th root, n things, the nth root. We want to be careful, though, to make sure that we do have 1-to-1 stoichiometric ratios when we're doing this, because if we don't have 1-to-1 stoichiometric ratios like we do, we then have to consider the stoichiometric coefficients. The stoichiometric coefficients get multiplied by the variable and raised to that variable. So if I had something, if SO4 had 2 equivalents to barium's 1 equivalent, that's not the case. But if it was, say we had sodium instead of barium, we'd have twice as many sodiums as we do, sulfates. We would then have to multiply the concentration by 2 and then square that value. But that's not this problem. We're not going to do complicated KSP problems because they're essentially just algebra problems. And this isn't an algebra class. You should know how to do algebra, but we're focused on the chemistry. So we said we're going to focus on equilibrium, and we'll mention some things about kinetics. Well, kinetics is how things happen. Equilibrium is what happens. Activation energy is related to the kinetics. How does this thing happen? If the activation is lower, you have a lower amount of energy that's required for the reaction to proceed, so it'll happen a little bit faster, on average. There are always exceptions to this, but, lower the activation energy, the faster the reaction. Higher the activation energy, the slower the reaction. This does not relate to equilibrium. You can have a very fast reaction that has a very poor equilibrium. You can have a very slow reaction that has a very favorable equilibrium. They're not inherently related to each other, but sometimes, they're synonymous with each other. So, just what we said, higher energy, slower rate, so forth and so on. We use these type of energy landscapes to represent where reactions start in terms of energy and where they finish in energy. And so because the reactants start at a higher energy than the products, we can call this an exothermic reaction. The difference between the starting material's starting position and the product's ending position, that is the delta H, or the enthalpy of this reaction, which, since it's less, has to be negative. This amount of space or this energy above the starting material is the activation energy. We have to overcome some activation energy before we reach the products. The activation energy, or the transition state that we find at the peak of this activation energy, is the highest energy species in the entire chemical reaction. That's how we define what the activation energy is. It's how much energy do I need to reach the highest energy species, intermediate, transition state. They're all similar words that mean the same thing, is that we have to pass through some point. The highest energy point is the determining factor of whether or not the chemical reaction occurs. So we've kind of already mentioned this, but if we have a poorly favored reaction or something that just isn't going at the speed we want, is there anything you can do to it? Well, temperature is related to internal energy, so we obviously should be able to add some temperatures. That'll make the reaction go faster. Might disfavor the equilibrium we're targeting, but we can always speed up or slow down reactions to kind of protect or be certain of what's going on. And so, in general, if we increase the concentration or the pressure, we'll increase the reaction rate. If we increase the temperature, we'll increase the reaction rate. Now, increasing these might disfavor the equilibrium. So if we have an exothermic reaction, if we increase temperature, the reaction is going to happen faster, but it's also going to happen to a lesser extent. Likewise, if we have, some gaseous reaction that makes more molecules of gas than it starts with, well, pressure will make that go faster because it's forcing everything to happen, but it'll happen to a lesser extent because pressure disfavors more molecules in the gas phase. The other thing that we haven't mentioned is a catalyst. A catalyst is some spectator molecule that just watches the reaction occur, but changes how it happens. So it doesn't change itself. The catalyst remains unchanged from the beginning to the end of the process. Now, it might shift a little bit during the process, but at the beginning and the end, it's unchanged. The same exact material. All it does is it modulates the activation energy. For a successful catalyst, it lowers the activation energy, but if you have what we call inhibitors, that's a catalyst that raises the activation energy. So a catalyst is just something that changes the activation energy. If it lowers it, we say that's a favorable catalyst. If it raises it, we say that's an unfavorable catalyst or an inhibitor. We have lots of inhibitors in the body. Once a certain amount of concentration of some protein has been made, the body doesn't want to make any more, so it has some type of inhibitor or catalyst enzyme that prevents the production of said protein. So the catalyst doesn't change the energy, it just changes the pathway. And so instead of having to go all the way over this hill and then down, you can instead go across the hill. A little bit easier path. You don't have to reach such a high energy. Now, sometimes catalysts change the reaction pathway so much that you can't relate the initial uncatalyzed reaction to the catalyzed reaction. If the uncatalyzed reaction is a one-step reaction, but the uncatalyzed reaction, because of that catalyst, becomes a 20-step reaction, it's going to be very difficult to correlate those rates just off first principles. You'll actually have to have experimental, information. And so generally, a catalyst will increase the rate of reaction, but that is not 100% true. There are plenty of cases where that, is wrong because the catalyst then ends up going through some alternate pathway. That alternate pathway can be entirely different than the initial pathway. And so the effect of the catalyst is just modulating the activation energy. Pretty much everything that we call catalyst lowers the activation energy. If it raises the activation energy, we typically call it an inhibitor. Enzymes are the best catalysts that exist. They're catalysts that have evolved over, time, whether that be, minutes, seconds, hours, or millions and billions of years. They've had plenty of time to evolve to do the most precise chemistry possible. And so what we see is that, catalysts will lower the activation energy by a good amount. Enzymes will lower it even more, and the selectivity of the enzyme versus a catalyst is very specific. A catalyst might affect a whole bunch of different transitions, whereas an enzyme affects one specific transition. Because it's so specific, it's also incredibly efficient. So we have some type of ligase enzyme that separates sucrose and glucose, or fructose and glucose, from the sucrose parent molecule. This linkage bond is an oxygen-carbon bond. There are 6 oxygen-carbon bonds in glucose and fructose alone. There's one extra oxygen-carbon bond that's in sucrose. That is the only bond that is targeted by this ligase enzyme. And it's a very specific, very favorable reaction. The reason for this is we have these very complex enzymes that essentially have binding pockets or active sites. These binding pockets are shaped to the molecule that they're to interact with. Because of this shape compatibility, they only interact with specific sites of the molecule and then can have reactivity at very site-specific locations. This is how biology works, is the use and clever engineering of millions and billions of enzymes to cause everything that happens that we observe and feel. So we talked about a whole bunch of things. The focus was equilibrium. Equilibrium is defined as when the forward rate equals the reverse rate. This is, sometimes more, complexly referred to as dynamic chemical equilibrium. It's just referred to as equilibrium by most people when we're not, teaching it for the first time to introductory students. We talked about kinetics, but kinetics is the how. We only really care about the what. Le Chatelier's principle tells us how we can shift what happens. If we apply a stress to one side of the reaction will shift away from that stress. If I stress the products, I'll shift to the starting materials. If I stress the starting materials, I'll shift towards the products. KSP is just another specialized equilibrium constant for the solubility of some, material, whether that's a salt, covalent compound, doesn't matter, just the solubility of any species. We had, Kw, which was a specialized equilibrium constant for the autoprotolization of water. We're going to use a whole bunch of generalized KEQs, which is just the products raised to their stoichiometric coefficients, divided by the starting materials raised to their stoichiometric coefficients. We talked about some activation energy, catalysts, things that can modulate or affect how the reactions occur, but these don't affect what happens. The main focus of equilibrium is what happens. In this chapter, we want to focus on equilibrium. Kinetics is how it happens. We're not as focused on the kinetics because that's very complicated, requires a whole lot more math than we're able to deal with at this point in time. So really, focus on reaction rates in terms of kinetics. That's the only thing I'm going to really ask you about kinetics is reaction rates. Equilibrium and the calculations associated with that is going to be the biggest main focus. I introduced the challenge problem for this question in lab this week, so make sure that you review that. Le Chatelier's principle is just how we can shift equilibrium given some stressor. If you have any questions about this, make sure you reach out to me. We will be having an exam next week, so look forward to the next video, as well as reaching out if you have any questions.